Hello, everyone. Welcome to a brand new lecture. So we're going to do just like we did in chapter one, except we're going to do multiple parts on this one. We're going to start off by looking at the general chemistry. Then we'll go into some more the organic chemistry. So at least two parts. It could be more parts than I expect, depending on how editing goes. But let's see and get started. All my classes always begin every lecture with a quote, and this one says, "If there is no struggle, there is no progress." So remember, even if you are struggling, it's because you're progressing towards something. So as we get started, my students will know that they needed to be discussing and understanding every one of these objectives for each of these sections. So let's really jump into this and get an idea of why we are doing chemistry in an anatomy and physiology course. A lot of people will brush over chapters 2 and 3, but they are the most important to understand physiology because physiology's main understanding comes with chemistry. Chemistry is kind of, think of physiology as highly controlled chemistry. Usually, when there's a problem with the patient, it's something chemical. There are acid levels, too many hydrogen ions, for example, or not enough, too many or too few ions, the things that we're going to discuss in this chapter. So, to really get an understanding of this, we have to understand first off the atom being the smallest stable unit of matter. Given that, matter is anything that has mass and takes up space. This would be things like solids, liquids, and gases that you've heard of before. There's some courses of mine that I'll talk more in detail about that, but not in this lecture. Now remember, atoms are composed of protons, neutrons, and electrons. Those are the three subatomic particles we saw in chapter 1. So let's get more into this. And first thing we want to look at is your basic atom. Now what we're going to do, we're going to discuss the three subatomic particles, protons, neutrons, and electrons. And we're going to look at their charges, their relative size, their mass, and their locations. So as we go through this, what we want to do is take a look at a basic kind of drawing here of your generalized atom and understand that an atom here, we have a nucleus in the center, the nucleus, and we're going to see that contains some subatomic particles. And then we're going to see some electron shells or orbits circling that. Okay, so in this nucleus, what do we see? What is going to be found in the nucleus? First off, we're going to see two subatomic particles, protons, who have a positive charge, P for proton, P for positive. They're very large. They're large and have a positive charge. And they have a mass of 1 atomic mass unit. That's what AMU stands for here, is atomic mass unit. And they're located in the nucleus, where neutrons are neutral. Another way to say neutral is they have no charge. Their charge is 0. They're large and have no charge. And these guys, being in the nucleus, also have a mass of 1 AMU. So this is going to be relatively important when we think about what it is going on in the nucleus, is where a majority of the mass is going to be. So you have protons in the nucleus and you have neutrons in the nucleus. Remember, neutrons have no charge, so if you thought about their charge being 0, it spells no. Protons are positive, P for positive, P for proton. So if we think about their relative charges, their charges here, we could put that in parentheses. Now, surrounding the nucleus is going to be electrons. Electrons are negatively charged, very small subatomic particles with very low mass. They do have a mass, they do weigh something, but their masses are so low that if I am ever giving you a calculation to do with this, we're not worrying or considering its mass. Now, with that, they're located in the electrons, in the electron cloud, in orbits or shells. So let's take a look at that. So what we would see is these electrons here, E negative, would be found in various shells surrounding the nucleus in what we call, now we think of this as a cloud, and I'll talk about that a little bit as we go along, that is somewhat of a cloud, an electron cloud, and discuss that. So let's get an idea of what's going on here. Now, As we think about the protons and the neutrons, remember they are in the nucleus of the atom. That is where the mass is going to be concentrated. Then we're going to have a cloud of electrons. Why do we represent it as a cloud? Because the electrons are going to be whizzing around so rapidly that we don't really know where they are, but we know the general space they take up. So we have a cloud. Now, there will be shells inside this cloud or orbit, so we will discuss later. Now, the electron cloud would surround everything. It would contain other electrons. Other electrons would be found here as well. So the electron cloud, here we have an electron here being surrounded by other electrons. So they are containing everything. All protons, neutrons, and electrons. The cloud does contain some other electrons, oftentimes. Not true for every element, but we're going to talk about that. Now, as we talk about that, as we're getting this idea, protons and neutrons, the number of protons is determined by looking at the atomic number on the periodic table. That is always the lowest number. The number of protons by the lowest number called the atomic number. Now, this is something very important when it comes to elements, is that elements, atoms, they will have the same number of protons and electrons. They are equal in all normal atoms. Every atom on the periodic table will always have the same number. Now, let's say that I were to look at a basic number line here. And on this number line, I have 0. And let's say I have on both sides of this, I have -1 and 1. These two integers. Now, these two integers being whole numbers are the same distance from 0. So if I add them together, it will create 0. If I were to have -10 and +10, again, same distance. When you add those together, again, you get 0. When you have the same number of positives and negatives, they cancel each other out. So what we have going on here, guys, the same thing, is that if protons and electrons are equal in an atom has no charge because the negatives and the positives cancel each other out. There will be neutral. So all atoms are fundamentally neutral. And an element is just where every atom is the same atom. You would have a pure substance where if it's sodium, elemental sodium, then every atom is a sodium atom. If it's carbon, every atom is a carbon atom. If it's calcium, every atom is a calcium atom. If it's a mixture, some other kinds of things, this gets in the realm of molecules. And so we're looking at something different here. We're looking at pure. Every atom's the same atom. You can't break it down any smaller than the atom and have the same property. Now, what we're also going to see is that the mass of an atom is mostly going to be determined by protons and neutrons. Remember, the protons weigh 1 AMU and the neutrons weigh 1 AMU. So given that, you're going to see that if I add together the protons and the neutrons, I get the mass of an atom. Well, we get something very interesting here. If I ever need to know the atomic mass, the sum of protons and neutrons, well, how am I ever going to find out the number of neutrons? Because here's the deal. If I were to look at the periodic table, let's say I have a tile here and I have hydrogen. Well, hydrogen's atomic number is 1. Now, if you look at the bottom of a hydrogen atom, you'll see something that says 1.008. I'm looking at my periodic table on the wall in my office here. And this says a lot of information. Now, well, the information this is giving me, the atomic number, remember, is always the lowest, is the atomic number. Now, this number down here is the atomic weight. We will talk more about atomic weight in a minute. We can, from the atomic weight, infer the mass. And what I'm just going to say is we'll keep this a little bit simple for now. We will be able to do that in a minute. But let's say I have an atom an atom's mass were to equal 1. Well, from this, we know that mass is equal to the number of protons plus the number of neutrons. Well, here's the problem. If 1 equals the number of protons plus neutrons, well, the atomic mass, if it's 1, and let's say I also gave an atomic number that equaled 1. This tells me that the number of protons equals 1 and the number of electrons equals 1. Okay, so we got this. The atomic number, we need the atomic number and the atomic mass of an atom, and its atomic number to gain enough information to figure out neutrons. Well, let's plug that in. 1 equals 1 plus n being the number of neutrons here. We now have to figure out how many neutrons we have. Well, basic arithmetic says that if I want to get something that I'm adding to something away, I have to subtract it from the other side. So now n equals 1 minus 1. N equals the mass minus the number of protons. So in this case, N equals 0. There are no neutrons for this atom, for hydrogen. If we look back, we have a weight that's a little higher than the mass of this atom, and we're going to see why that matters in a minute. Now, let's say again that I had a mass of an atom that was 12 and an atomic number that was equal to 6. Okay, and that means here, so 12 equals 6 plus the number of neutrons. Given that, 12 minus 6 equals the neutrons. And that would say what? That we have 6 neutrons. So I'm just writing it a little bit differently, same principle. Okay, so what you're going to do is anytime you ever need to find the number of neutrons, you take your atomic mass, subtract the atomic number from that. So the atomic mass can be extrapolated. What do I mean by that? And I'll talk about that in a minute as we get to atomic weight. Now, also, there's some elements out there that are essential for living things, and we would say 96.3% of the important essential elements fall into 4 different elements. These 4 are the most abundant, and this is what most of your body's made up of. 96.3% of your body is carbon, hydrogen, oxygen, and nitrogen. Now, that is not relative abundance in listing. But shown is an easy thing to remember. We're going to see more about this in a minute. Now, there are some that are needed in a few, they're needed, they're important, they're just needed in fewer numbers. And then there is even less, where if you add them together, they're not even a percent of overall body's mass, would be the trace elements. They are even smaller levels, like iodine, for example. Now, as we look at this, we would see that 96% CHON. Oxygen is 65% of your body's mass. Then next to that is carbon, CHO and N. Hydrogen, and then nitrogen. This added together is about 96.8% roughly of the mass of a body, of most living things. Then things like calcium, phosphorus, potassium, magnesium, sulfur, iodine. These things are needed in very small numbers. But then you get down to your trace elements. Trace elements are things like selenium. Now, selenium is needed in very small numbers, and there is the existence of selenium on some amino acids. You get too much of it, you get selenium poisoning. But we don't need much tin. We don't need much chromium. We don't need much vanadium or boron or aluminum. Our body has these things, but in very small numbers. And if you actually add them up, they're about 0.001%, around there. So they're much less. Okay. Now, we were going to be talking about the difference in mass and weight in a minute. So we're going to talk about that in just a minute. Well, to understand that, we have to understand one more thing, that there are atoms out there who have different numbers of neutrons. They have the same number of protons, different number of neutrons. So that neutron number being different makes them an isotope. These isotopes are oftentimes unstable. Some isotopes, not all, who have extra neutrons become unstable. When they become unstable, they may emit radiation. They're called radioisotopes. And how long it takes half that to decay is called its half-life. Now, case in point, here we have a normal hydrogen atom, hydrogen 1. This is the most abundant one. Then we go look at hydrogen 2, who's a little bit less in number, and then hydrogen 3, who's even more less in number. We would see hydrogen, deuterium, tritium. See the fact that normal hydrogen doesn't have a neutron, but here deuterium does, hydrogen 2, so it has a mass of 2. 1 AMU for the proton, 1 AMU for the neutron. Tritium, 1 AMU for the proton, and then here the 2 extra AMUs for each, 1 AMU for each of the extra neutrons. So this 3 representing a mass of 3, this 2 representing a mass of 2, this 1 representing a mass of 1. Now, this gives us something very important, is there are the atomic mass. The mass is the sum of protons and neutrons. So when we saw that 6 protons, 6 neutrons, 6 electrons, the electrons who have very small mass isn't really contributing very much, so we would say the atomic mass is 12 daltons. In the atomic weight, it's the average mass of all the atoms and their isotopes. Now think of it like this. Let's say your professor comes in and says that the class average for an exam was very low, a very low class average. Well, what that is saying is that it's not saying that people didn't do well. It's just saying a lot of people did very poor. That there was maybe a lot of very low exams, but not showing that low average isn't showing that somebody maybe made a 100 on that exam. So that 100 was very few in number, very low amount of people who did exceptionally well, where most people did very poor. So if we have isotopes who weigh extra, they have the extra mass because of the extra neutrons. On average, there are very few of them in nature. So the average mass is only put up slightly, kind of as if someone did very well on an exam, their high grade barely affected the average for the class because most students did very poor. So we use mass and weight. We use a unit called Dalton. Daltons. I'm not going to really hammer on that much. Now, as we talk about moles, moles are basically telling us how many atoms we have. If I have an amount of an element equal to its atomic weight, especially when you're dealing with molecules. In molecules, the average mass of all isotopes for a normal element. Now, we also can see a mole is an expression of that, used grams in that we use. So this is just how much of an element is equal to atomic weight. This is why when we have a molecule and we're having how many moles per gram, how many grams per mole do we have, we're basically getting a calculation of how many atoms. Now, this periodic table, if you guys would like to have a copy of that, you can easily go find it at webelements.com. This is the one that I use for my classes. I find them to be really good. They are open educational resources as long as we credit the source. It's right here, webelements.com. Their printable periodic table gives you a key of what everything means. So I really like this one. So let's take a look at some more information. And this is where we're going to get into some more quality of teaching, I think, is let's discuss the electrons, their shells, and orbits. Now, it's going to be the electrons that are going to help determine reactivity, specifically those in the outermost shell. And that outermost shell is called a valence shell. Now, valence shells can be any shell. So if I have a nucleus here, here's my nucleus of an atom. And around that, we can have a variety of shells. So let's say we have shell 1, shell 2. Let's even add a shell 3 for this example. If we have 3 shells, this shell here is called the valence shell. Now, what if I were to remove that? What if we were to get rid of that? Sometimes this thing is a pain. It doesn't really want to do what it's supposed to do here. Um, the app I'm using to try to draw with is not letting me erase. So anyway, I'll just do it this way. So if we had the nucleus here and we had 1, 2 shells, the second shell would be the valence shell. And if we had only 1 shell here, the first shell would be the valence shell, the outermost shell. So it's just whatever shell's on the outside, and I'm going to show you how to figure that out in just a moment. So I'm getting kind of the terminologies down. Now what we're going to see is with this, the electrons of the outer shell is called the valence electrons, and that's going to determine whether or not it is reactive or not reactive. Another way to say not reactive is to say it's inert. Now, let's say that we were to go out to a restaurant and eat. And here in America, they have some of these places where, like a steak challenge, that if you eat a steak that is this massive steak, and if you can eat the whole thing, it's free. That the steak is so big, if you can eat the whole thing and finish it under a certain time, like an hour, then your meal is free. If not, it's going to be a very expensive steak. It's a large, expensive piece of beef. Now, given that, let's say that person comes in and they eat it, they finish it, and the owner of the restaurant comes out and said, never seen one do this before, you get a free steak. And the person's like, no, I can't. I'm so full, I can't take any more steak. And there's somebody else at the table because this person ate that steak all by themselves. They didn't get enough food, and they're really hungry. So they'll be the one wanting to take that steak. I always use the example in my class that if we went to the pizza buffet that's nearby the college and we were to go eat pizza, and one of my students ate all the pizza, and one of the other students didn't get any because the student ate it, and the owner of the restaurant came out and said, I've never seen a person eat so much pizza, here's a free pizza. And the student who ate all the pizza says, I am so full, I can't hold any more, I don't want it. And then the student who didn't get any pizza, who didn't get to eat enough pizza because the other student ate it all, grabbed it to eat it because they were not full. They were hungry. They didn't have enough to eat. They wanted to fill up. So what happens is if a shell is full, the outer shell is full, the atom will not react. It's inert. And so a filled outer shell means atoms will not react. If the outer shell is unfulfilled, it will react. Kind of like if you're full of pizza and you do not, and you've had all the pizza you can stand and they give you free pizza, you will not eat any more pizza. You can't hold it. But if you did not get enough pizza and you are hungry, you will take that until you get fulfilled. So an unfulfilled shell means the atom is reactive because the outer shell is not full. Now, the outer shells, sometimes we also call them energy levels. They have a maximum number of electrons they can hold. We will start filling from the inner shells, lower shells, those closest to the nucleus, and move outwards to those further from the nucleus. And let's see how we do this. Now, I'm going to look at this and do it this way. Let's imagine the nucleus here is the science building at your college. And you are driving in, you're commuting to college, you want to park as close as you possibly can to the science building because that's important that you park nearby. So you want to park to the closest parking lot you can. Well, as it turns out, parking lot number 1 here which is found near shell number 1, found near the nucleus, the science building, only has room for 2 cars. So 1, 2 can go here. Now, if you wanted to park next to the science building, the nucleus, and can't because it's full, the parking lot's full, there's already 2 cars in that lot, you have to go park off further away, go a little further off, and this lot, lot number 2, can hold up to 8 electrons, 8 cars. So 2, 4, 6, 8. Now, once it's full, you have to go to a lot further out. Even further away from the science building, you got to park. Let's say lot 3. Now, lot 3 can hold 8, and then after argon, it can hold up to 18. 8, but after argon, 18. So before argon, it can only hold up to 8 electrons. Now, for my class, we won't go past argon for electrons, but I hope that makes sense. So what we're going to do is the maximum amount. There's only so many electrons each shell can hold, like a parking lot. The first shell can hold up to 2. Once it's full, you must go to the second shell. Second shell can hold up to 8. Now, the maximum the third shell can hold is 18 after argon, but up to 8. And my students only have to know up to argon. Past argon, we don't have to know electron configurations past argon in this class. All right, so let's use this information a little bit. So let's practice this a little bit. If you have the periodic table handy for your lecture, let's just say that we take an element here. Let's use a very common element, carbon. And carbon has an atomic number of 6. And let's just say mass is 12. Mass is 12. 12 point something. Okay, so atomic number is 6. That means we have 6 protons and 6 electrons to deal with. So let's take carbon atom, the nucleus, and let's take shell number 1. Now, we have 6 electrons to deal with. The first shell or orbit can hold no more than 2. So, it's definitely going to be full. 6 electrons minus 2 electrons equals 4 electrons left to play with, okay? That is 4 electrons we have left to play with. So now we can go to the second shell here, to the second shell, and in the second shell, put the 4 electrons. Now I'm going to put them like this in my drawing, but now that means here that we could see 2 things. First off, the valence shell here, VS, has 4 valence electrons. Okay, so we could see how many valence electrons we have. We can also tell that this atom is reactive because the valence shell is not full. So we have those 2 things. Let's take another one here. Let's take sodium. Sodium atom. On sodium, we have an atomic number of 11. Now, with sodium atom, let's take this and let's build sodium. Now, of course, we have 11 electrons to play with. We've taken away 2. And this is leaving us with 9 electrons left to play with. So now, with 9 electrons left to play with, we know the second shell can hold up to 8 electrons. We have 9, so that's plenty enough to fill shell number 2 with 8 electrons. So now 9 electrons minus 8 electrons leaves us with 1 electron left. And that 1 electron is going to go out to the third shell here, all by itself. Okay. So now that we've practiced two of these so far, that really should make a little bit more sense to you. So remember, if a valence shell is unfulfilled, it wants more electrons. It needs more electrons to become fulfilled. So the atom, when it has a maximum number of electrons in its valence shell, it's inert. Atoms are trying to get to this if they can, and this is what's going to determine whether they bond or not. All right, and that really takes us here to compounds, molecules, and things like that. What I'm thinking about doing is doing this in a 4-part series so that we can talk about chemical bonds and then do water chemistry and then organic chemistry. So I'm going to go ahead, guys, and end this here, do this in a 4-part lecture. This concludes my first part of Chapter 2. I will be doing more of these now that I'm back, now that I got some things completed. Thank you so much for watching. I hope you find this helpful. Let me know future videos you would like to see me do. And as always, thanks for watching.